Now, any questions? No? You unmuted yourself for nothing? Okay, so it seems to be no questions. We're on, this is 16.3.4. This is Green's theorem. Actually, let's just quickly chat about this quiz problem. We're going to Green's theorem.
Excuse me, is there a reason your inset screen is smaller than the full screen? Can we fix that somehow?
What do you mean? You want the paper to be bigger?
Yeah, that screen is just a subset of my full screen on my computer, at least. I don't know how everybody else is seeing it. But it's smaller than it's been in previous weeks. Let me see, I can probably change the boundary. Yeah, okay.
Yeah, mine is full screen on my computer.
I can change the boundary myself. And so can others if they need it.
Okay. I think I can zoom, but this way we get a good view of the whole page. Did we prefer this setup or last week's setup?
It's better now, thanks.
We got a top view, so it's not as weirdly skewed as last time.
There's a boundary bar between like the people videos and the subject matter.
Oh yeah, okay.
We can move that ourselves.
Yeah. Okay, so the problem wanted to integrate from 102 to 463, and f is yzi plus xzj plus xy plus 2zk. So we could do this a variety of ways. What's the first thing you thought about?
Like a line integral?
Yeah, I mean, how do we compute this line integral?
I wrote out the formula first.
So we could do that. We could find a parameterization, parameterize, and then we do something like this. Right, that's from 16.2. We can use that technique. We could also use the fundamental theorem. We could use the fundamental theorem. That is, maybe if f equals, if gradient of f equals f, then the integral f dot dr is f of 463 minus f of 10 minus 2.
Yeah, I did that one.
If we have the fundamental theorem, or if we find such an f, we can do that. So either way is possible. I would probably go with this one. Assuming I can find this function f. Okay. So how do we start finding this function f? I'm going to do some integration here. This is p, this is q, this is w, call those w's, and this is the derivative with respect to x, the derivative with respect to y, and the derivative with respect to z. Okay. So I know that the integral of p dx is f of x by z. That's by definition of p. So if I integrate this with respect to x, I get f of x, y, z is this integral with respect to x. So that's x, y, z plus some function that has only z's and y's in it. Because when I take the derivative with respect to x, this could disappear.
Mhm.
Okay, so what do I do next?
You differentiate with respect to y.
Okay, I differentiate with respect to y. What do I get?
Xz plus g prime.
Plus g prime. G is a function of two variables, right? So we got to be a little more careful than that. We can say g dg dy,
Yeah.
right?
Well, it equals 0 anyway, but yeah.
Yeah, I was going to say that.
Yeah. In this case, it does equal 0. But in general, if we didn't have a immediately obvious thing where it's equal to 0, we would have to be a little more careful. And what is this equal to? This is equal to xz. And so dg dy is equal to 0, as we say. Right? So now we're still looking to find what g of yx z is. What does this tell us about g of yz?
I just named it a different function h of z as the integral of that.
Okay. Why did you say h of z? That just means that, well, you chose h of z because its derivative with respect to y is 0. That means this has no y's in it.
Yeah.
Right?
No y and
So
no
that's-
x. You
And
just
no
get
x.
to c.
And so
right?
that's why you can call it h of z, knowing that there's no x's or y's in it.
Yep.
Right? So this is 0. So g of yz only has z. We can rename it h of z. So f of x, y, z is x, y, z plus h of z. And how do we finish this?
You differentiate again.
Differentiate again with
to z.
respect to z. And we get xy plus h prime of z is equal to xy plus z. Is that a 2? Yes, 2. This is a very 2z. So h prime of z is 2z, and h of z is z squared plus some constant k. So our function f is xyz plus z squared plus k. So does k matter here?
No.
No, I can pick any value of k I want, still satisfies this. If I don't pick a different value of k, it gets removed. So pick your favorite k. My favorite one is 0. Okay, and then you evaluate this function. What do we get?
I got 77.
Okay, that seems reasonable.
Like all you have to do is just plug in 4, 6, and 3 into x, y, z plus z squared, right? Then
Yeah,
subtract it from 1, 0, -2.
We'll subtract 1, 0, -2 from it, but yeah. We got
Yeah, I'm
f.
sorry, I worded that wrong. Yeah.
We got f, and we just do that. Not hard.
Yeah, I got 77 from that.
Sounds reasonable. Does that make sense? So we could have done this, where we made a parameterization, took some derivatives, took some dot products.
I'd rather not.
I'd rather not. I don't think anyone did that. Okay.
I did.
Oh, okay.
Respect.
Well,
Not get 77 though.
yeah, it's a possibility.
Respect.
You should get the same answer. Any questions on that?
So was the answer 77 or not?
I have no idea. I mean, we could just put it in right now.
So,
All right. 4 times 6 times 3 minus 9 minus,
I've got
One.
77 and I did it with a calculator.
okay, that sounds good. Minus 2 minus 2 squared. That seems pretty big. I don't know. Someone put that in. That seems close to 77-ish. 6 times, which it's 18 times 4. 18 times 4 is 76. Minus 9 plus 4. Sure.
Yeah, 77.
Okay. Any questions on that before we move on? No? Okay. This is a nice application of the fundamental theorem. And I want to one more time emphasize why this is neat. I was given this. I'm traveling from this line segment to this line segment. But in theory, well, and in practice, this is the integral of any curve that travels from here to here. It does not matter what path I take from here to here. Okay, so if I had given you a really complicated path from here to here, this would be for sure the easier way to do it. And then I wouldn't have had to parameterize a really complicated path. Okay, so this is an important example leading into the next section. Well, I mean, not this particular example, but it showcases an important idea. You can compute these integrals in many different ways. Some of them are going to be easier, some of them are going to be harder, and it's not going to be the same way every time. Okay? So, let's look at Green's theorem. So, like I said, I think Green's theorem is, well, I haven't said that yet. I think Green's theorem is really cool. It has a lot of interesting applications that you don't really think about, that you never actually use to compute, but they function a lot. Another interesting thing about Green's theorem is that these theorems generalize to complex analysis very easily. Okay, so if you're interested in physics and you talk about complex numbers, which are fundamentally important in physics, you're going to need to know complex analysis, and complex analysis has its own application of Green's theorem, which is really nice. Okay, so what is Green's theorem? I want to one more time remind us of what we're doing. Right, we've got the fundamental theorem, the integral from a to b of f prime of t dt is f of b minus f of a. Okay, and I'm going to write this a lot of times because we want to say, like we did previously on the fundamental theorem for line integrals, that Green's theorem does a similar thing. So what do you think I'm going to say? It takes the stuff, an integral of the stuff on the inside, right, and turns it into a calculation of the stuff on the boundary. Okay, so let's see that in application in higher dimensions now. So before we were working with the lines and curves. Curves are dimension 1, just like this intervals. So the boundary was just the points on the end. But now our boundaries will have different shapes, and our regions will be 2-dimensional regions. Okay? We expand to higher dimensions. So what does that mean? Well, let's say I have some curve that does this, very complicated curve. And I want to compute a line integral on this curve. Well, using this idea of I can compute the stuff on the boundary by computing the stuff on the inside, I should be able to compute this line integral, the line integral along this curve, by instead transforming it into a normal double integral across this region. Does that make sense? This computes the stuff on the boundary and changes it to an integral across the interior. So the line integral on the boundary can be converted to an integral on the interior, which would be a double integral, right?
Do you like cut it in half and make two like a axis of symmetry or something like that?
We could chop it up and do a bunch of stuff, but we don't need to. So we'll see how we would do that in practice. So plan, convert the integral on the curve to an integral over the region D. Okay, so let's put a couple rules on what kind of curves I'm allowed to have, right? So what's the first thing you notice about this curve? What do we notice?
Not a function.
True, it is not a function.
Doesn't help.
That does not really answer our question. Let's talk about curves that we talked about before. We thought about them before. What's special about this curve? It starts and stops in the same place, essentially, right? It's closed. It goes in a big loop, right? So what are we going to want to talk about? In order to talk about a region, we need to have a closed curve, right? Because if it's not bounded, then we can't integrate over this really large, infinite, possibly infinite region, right? So we want a closed curve. And what does a closed curve mean? I.e., a curve that encloses a region. Right. This up here is not a closed curve. It doesn't enclose a region. Right? This is. And now these are a couple more technical-ish ones. We want it to be simple. And what does simple mean? Not overlapping. So this is simple right here, but this is not simple. This is closed, and it closes region, but it is not simple. Okay? And third, this one is somewhat trickier to observe. Well, not trickier to observe. We need to make sure it's oriented the right way. And orientation in this case means if I'm on my curve, I have to travel some direction, right? I can't just imagine I'm here, I'm traveling along the curve this way. Okay, that's what these arrows mean. So we want something that's positively oriented versus negatively oriented. So I want to define what positively oriented means. A positively oriented curve, this means as you travel the curve, the region is to your left. Okay, so imagine I was a little bug right here. I'm driving along this beltway, right? This is like the beltway here. Okay? And as I move this way along the direction of the arrows, the region is to my left. Correct? If I was going this way, the region would be to my right. So the positive orientation is the orientation where the region is to your left. Okay. In most cases, I'm going to say most, not technical most, that is counterclockwise. Okay. Does that make sense?
Professor, are we still talking about path independent functions as long as we're only moving in one direction at a time? Could be moving in a negative direction or a positive direction, but it can't be something like overlapping waves or overlapping sine curves that are moving alternatingly or at the same time between the two, correct?
I don't really understand what you're talking about here.
Well,
And
this is still not path dependent, is it?
yeah, well, let me clear up what we're talking about, and then maybe that should answer the question. We're not talking about, we don't have a function at all at the moment. Okay, all we have is a curve in the plane. So imagine that this is a map, and I'm literally sketching my running route on the map, right? Let's say I live here, and I'm just following this map because this is a nice little run, and eventually I want to get back to where I started. Okay, that's all we're talking about. We're not talking about any function on this curve yet, which is what you'd be talking about when we talk about path-independent functions or path-independent integrals.
So basically, we cannot use the arc length here because it's not a function.
We could use the arc length. We could integrate the normal line integral stuff, but it may be harder depending on what we're wanting to integrate.
Okay, but if you had a problem like this with a function, then it's just arc length. That's all we're doing.
It could just be arc length, but we haven't set up
Okay.
Green's theorem yet to see what we're exactly doing.
Okay.
Okay. We're just setting up the area in which we're integrating over. So any curves that have these three properties will be good curves. They're simple, closed, and positively oriented. Okay. These are the curves that we're going to look for in Green's theorem. So now, what does Green's theorem say? Green's theorem. Well, it says if C is a simple, positively oriented, closed curve, it needs to be smooth too, but piecewise smooth. So we didn't really talk about that, but that's perfectly reasonable. Bounding the region D, just like we had a curve that bounded that region inside. Then the integral, okay, I'm gonna write this over here instead. The integral of C, integral over C of these functions. Remember, we talked about this last time in section 16.2, right? We had a function. We want to integrate the line integral over just the x variable and just the y variable separately, right? if I want to integrate this on the curve, this is equivalent to doing a double integral over the region of their difference of the partial derivatives.
Is this curve just two-dimensional?
Well, curves are all one-dimensional, but
it's
it's in the plane.
yeah, right. So
Yes.
if it wasn't in the plane, like if it had some sort of z value.
Well, if it had some z value, it really doesn't bound a region in R3, right?
Hmm.
Then it would have this like weird shape in R3. So we're restricted to the plane at the moment because we need to
Okay.
actually bound a region.
All right. I'll
Right.
just wait.
So if we needed to bound a region in R3, we would need a surface, right? So let's take a look at what this means. So if I have this function, this curve, this is C, it's positively oriented, it is simple, it is closed, and it's smooth, right? And I have a function on C, f of x, y, and this is equal to pi plus qj. Right, we're setting this up just like we did before. And I wanted to compute this integral. If I wanted to compute that integral, it would be the same as computing this double integral over the region. Okay, so do we see why this is related to the fundamental theorem of calculus? Yes, no, maybe, I'm too lost to decide,
Yes.
to the too lost to decide, or? Okay, we'll see this in practice in examples in a little bit. I want to again remind you, I'm gonna say this a million times as we move forward the rest of the semester. We take stuff on the boundary and turn it into an integral over the interior, okay? Computation on the boundary over integral on the interior. So let's look at an example. I don't want to do an
That's why it's like the fundamental theory of calculus, right?
Yes.
The light went on, thanks.
Yeah, they're all going to be like that. The previous fundamental theorem of line integrals, stuff on the boundary, which were 2 points, over an integral over the inside. Normal fundamental theory of calculus. Integral over the interval is equal to the difference of the points on the boundary. So as we continue, all the fundamental theorems will do that. Okay? Do I want to do an example right here? It's kind of small. Is there enough space? No, I'll do it on a new page. Okay, so let's look at this function. Nice example here. So compute the integral over this curve dx plus xy dy, where c is below 1, 1. Okay, so this is our region C, or this is our curve C. And our region D is inside. Okay. So now let's take a check. Is C closed?
Yes.
Yeah.
Is it simple?
Yes.
Yes. Is it positively oriented?
No.
Yes. But why is it positively oriented? Remember, think about positive orientation as I'm on this curve, and as I travel in the direction of the arrows, the domain is to my left, right? So if I'm traveling like this along the blue arrows, the domain is to my left. If I travel opposite the blue arrows on the red arrows, the domain is to my right. So the blue arrows are positive orientation and the red arrows are negative orientation. Okay? Any questions on that? Remember, most of the time, if the curve encloses a region, it's going to be counterclockwise will be the positive orientation. Okay? If the domain encloses a region, counterclockwise will be the positive orientation. So how do we compute this integral? What are we going to do? If I wanted to use normal stuff that we did before, what would we do? We would parameterize this curve C, right? Into how many different curves? Into 3 different curves. We'd have to set up 3 different integrals because these are sharp corners. So we would set up 3 different integrals and compute 3 different integrals and then add them together, right? But using Green's theorem, we have instead, this integral is equal to the integral of the region D of D, this is Q, and this is P. So dq dx, which is y, minus dp dy, which is 0, dA. So instead of computing this line integral, which would be 3 line integrals, we're actually computing 1 double integral, which is quite easy.
Is dq dx, that's y, and then dp dy is 0.
Yes.
And so dq dx is just the derivative of q with respect to x.
Exactly.
You're subtracting that from the derivative of p with respect to y.
I'm subtracting the derivative of p with respect to y from it.
From it.
Yes.
You have it, so that double integral, the double integral of dq dx minus dp dy, that's equal to the integral of p dx plus dy. That dx and that dy and the normal integral, does it become like dq?
In what normal integral? This normal integral?
No. You gave us a definition. The double integral is equal to a normal integral.
Here?
Yeah, there. That says p dx plus q dy. Yeah?
Yep, p dx q dy.
So you're taking the derivative of p with respect to y times dx?
No.
No?
There's no times dx. P is just a function. It has x's and y's in it.
So why, I'm just confused on why they would be why is it that that is equal to, like, I'm confused as why they're equal to each other then.
Why these two things are equal to each other?
Yeah.
So this is the entire content of Green's theorem. If I have these conditions on C, and the derivatives of P and Q are continuous, I have this equality. That's it. That's just Green's theorem in action. So there's a proof in the book of a simpler version of it. It's a pretty complex theorem to prove. I can't really give you I definitely can't give you a proof without going through it, but I can give you some sort of like intuitive understanding, right? And so I'll attempt to give you some intuitive understanding. Who knows if I can actually do it or not. Let's think about this. Just this part. When I do an integral, what does it undo? It kind of undoes this derivative, right?
Yeah.
So imagine taking this integral to each of these things, and I should get the appropriate thing back. Right?
Yeah, okay.
So just like the fundamental theorem, where we had this, I introduce a derivative, but also an integral, which allows me to compute the stuff on the edge. So what I've done is added another integral. Well, let's say this instead of this. I've used an easier function to integrate, right? The derivative is usually simpler than the function itself, right? At the cost of another integral. So this has one integral and a possibly very complex function. This has easier functions, but two integrals. Does that make sense?
Yeah, that makes a bit more sense.
And we can see that here. Doing this integral, this is kind of nasty to integrate, right? I'd have to parameterize it a bunch of times, 3 different parameterizations over this curve C. But this is 2 integrals, but this function is very easy, and the region is also very easy to deal with, right? So we could deal with this pretty easily. How do we compute this integral? Right? We just now go back to chapter 15 on normal double integrals, right? This would be x goes from 0 to 1, y goes from 0 to 1 minus x. So our integral looks like 0 to 1, 0 to 1 minus x of y dy dx. And this is a very easy integral for us to compute, right? Does that make sense?
Our regions can get more, our regions can get more complex though.
Of course. Remember, the region and the curve are tied together, right? If the curve gets really complex, the region might get really complex. Right? The region is what's inside the curve. So they are inherently tied together. That's why Green's theorem, that's why this works as a whole. Something over the inside related to something over the outside. Okay? So we can compute this. I don't know what that number is. I don't know. I'm gonna guess. Maybe a half, a third, probably a third or something like that. Don't quote me on that, but we all can compute this. Okay. Any questions on why we did this? So that's not a new page. Let's look at another example. Okay. I've got something that looks like this. Oh, note, I should probably put this over here because I forgot to tell you guys that. It will go here. Note, often this symbol describes an integral over a closed curve. Okay, it's a normal integral with an extra circle in it, the circle in the middle. Often, this is also the symbol for a contour integral. Okay. So I'm going to do this integral. That's looks hideous, but that integral. 3y e to the sine x dx plus 7 plus dy. That's pretty nasty. And my region will be this. Okay. Is this simple and closed?
Yeah.
Yeah. Is it positively oriented?
Yes.
Yes. Domain is on the left. So we can use Green's theorem, right? So what does Green's theorem say? Let's go use Green's theorem. This integral is equal to the double integral over d of the derivative of this with respect to x. That's a typo, excuse me. What is the derivative of this with respect to x?
Seven.
Is
7.
that, yeah, is that y to the y?
Y to the 4.
Oh, to the 4, okay.
It could be y to the y. It doesn't even matter if it's y to the y because it doesn't have x's in it.
No,
So you
I
take
know. Yeah.
7 minus, what's this derivative?
Is that e to the 5 ln x?
It's e to the sine x.
Oh,
But it could be e to the
okay.
5 ln whatever x, because this derivative is actually 3. dA. So I took this extremely hideous integral. I mean, I have 0 chance of computing this integral. Even over this really nice curve. 0 chance of doing this. But at the cost of an extra integral sign, I instead integrate a really easy function. This function is 4. Right? So this is just 4 times the integral of the circle over the circle. And this is, what, 4 times the area of the circle, right? So it's 4 times pi r squared, which is 3, so 9, 36 pi.
How did they even come up with this? It's so weird.
How did Green decide this was true? I don't know, to be honest, historically speaking.
It's an inspiring story. It's in the book. He was a baker's son.
Oh,
Math on his own. He didn't even think about going to college till his father died when he was 29. He studied for 4 years to get into Cambridge, and then he died just a few years after that. And this work didn't get published until decades later by Lord Kelvin, whom we know from the Kelvin scale.
well, cool. That's
It's
Some people-
sad, but
yeah.
it's
Well,
cool.
that's very common actually. Lots of interesting old math is not really realized until much later. But how he observed this, I don't know. I would say some people have these magical. There's 2 kinds of things that are difficult here. The first is knowing that this is true or believing it's true to even go start trying to prove it. And then there's proving that it's true, right? Some people have a unique skill to just know what should be proven. And then some people go and prove them, right? So I don't know if Green wrote a complete proof for this. I actually doubt he did. I doubt I'm sure I'm not sure. I'm going to assume he probably knew this rule to be true and then proved it maybe in a couple small places. And then later along the line, mathematicians decided to prove that this is actually true.
He actually did publish a proof, and he published it in just, private edition that he could somehow pay for out of his own money, about 100 copies. Somehow it came to the attention of Lord Harewood, and once it was published, this provided the basis for Maxwell's equations and a lot of other.
Yeah. Green's theorem is fundamental in the history of physics. So it's also fundamental in imaging and biology and things like that, right? A very common question is, how big is this tumor? Tumors are weirdly shaped, right? And so a very common way to measure surface area, which we're going to talk about right now, is use Green's theorem. Okay? So there are objects that measure surface area. What are they called? They're called planimeter. They're these mechanical objects that do this, and they trace a curve. And they use Green's theorem to tell you the surface area. So they use those kinds of tools and techniques. They don't really have the metal objects anymore, but computers use these to use Green's theorem to tell you how big a tumor is, right? Map things use these to tell you how much surface area this thing has on the map, right? So the formula itself is extremely important, even though the physical objects that use Green's theorem aren't really around anymore. I mean, they're still around, but we don't really use them anymore. We use a computer. Okay, so let's talk about surface area. So in these previous two examples, what did we do? We observed that the integral over the curve was much, much, much harder to do than the integral over that region, right? This is easy, this was hard, but that's not always the case, right? So let's say I have a really complicated region. It looks like this. So obviously, computing equations to integrate over this region are hard, right? Because I'd have to make slices, I'd have to think about this, and then that, and that kind of stuff. But tracing this region is very easy, right? I mean, I just traced it. And furthermore, if I had a computer, for example, or some other object that made measurements of where my pen was at a certain time, I could easily parameterize this curve, the boundary, right? Because I know exactly where my pen is at any given time. That's exactly what a parameterization is. So if I get a parameterization, I can use Green's theorem to compute the area. And so how are we going to do that? What is the area here? What kind of integral describes this area? This one, right? The integral over d of 1 dA is equal to the area, right? Not super sophisticated. So if we want to use Green's theorem, what does that tell us to do? It says all we need to do is find some functions that have this property when I take their derivatives. right? So to compute area, we need to find P and Q such that, what does the inside of Green's theorem say? dq dx minus dp dy is equal to 1. Right? Because what is Green's theorem? I want this thing to be equal to 1 if I'm computing the surface area. Right? So all I got to do is find some functions that make that happen. Right? Not super hard, and there's lots of choices. Some choices are p equals 0, q equals x. The derivative of p with respect to y is 0. The derivative of q with respect to x is 1. Check. P equals minus y, q equals 0. Check. We can do complicated stuff too. P equals 1/2 y. There should be a negative sign. Q equals 1/2 x. More stuff. You can have lots of choices, right? And the reason I bring up more stuff is most of the time, well, most of the time these will be fine. But you may get a choice where a different function is better depending on your curve. Right? So let's see this in practice. Let's write this again. The area is the integral over the closed curve of x dy, which is equal to the integral over this closed curve of y dx, which is equal to the integral over this closed curve of 1/2
1.
y. 1/2, 1 second, p, this is p, minus dx minus, this has got to be a y. Yeah, that's a y. Dx plus 1/2 x dy. Okay. So we have lots of ways to compute surface area. Now we have an area, we can compute area using a line integral instead. Okay, let's see this in practice. Compute the area of the ellipse x squared over a squared plus y squared over b squared equals 1. Okay. Anybody know the area of an ellipse? No, I don't know the area of an ellipse. Anybody know the parameterization of an ellipse?
Sine and cosine, you can use those.
Yep, there are sines and cosines, right? It's pretty easy to parameterize an ellipse. R of t equals a cosine t, b sine t. This parameterizes that ellipse. Okay? So if I want to integrate over d1 dA, this is going to be equal to the area of this ellipse. So that's not A, B, B. Right? If I wanted to compute this integral, it'd be kind of a tricky integral to compute, right? I would have to separate this region into two regions, compute two integrals because it's not really a function. And then I'd have some weird equations with square roots in them and stuff. And it's not circular perfectly, so my polar coordinate transformation wouldn't be super awesome. It'd be okay, right? It would be doable, not super easy, right? Instead, we'll compute this line integral using Green's theorem. And it says the integral over d of 1 dA is equal to, I'm going to pick, so I have three different things I can pick here. I can pick this one. I can pick this one or this one, these sets of P's and Q's, right? I'm going to pick this choice of P and Q. Okay? Why? You'll see. But I could pick any of them and it'd be perfectly the same. So this is equal to the integral, I'm gonna have a half here, of over C of minus y dx plus x dy. I have a parameterization already, right? A cosine t, b sine t. So r prime is minus a sine t, b cosine t, right? So how do I compute this? I just go at it the classic way. And it's 1/2. I put these in for x's and y's. T less than or equal to 0, less than or equal to 2 pi. 0 to 2 pi of, this is y, so minus b sine t, sine t, yeah, that's fine, times dr dx, x prime of t, that should be written x prime of t, plus x, which is a cosine of t, times y prime of t, dt.
Is x prime of t the dx portion?
Yep.
Okay. And y prime of t is the dy portion?
Yeah, because this is x and this is y.
Gotcha.
So minus b a sine squared t plus, that's a plus sign because I have a negative sign there, a b cosine squared t dt. This is 1/2 integral from 0 to 2 pi of ba dt. So that's just 2 pi ba over 2.
Could you explain what happened to the x prime of t and the y prime of t?
X prime of t is minus a cosine t, right?
Oh, I see.
So this has a squared on it because I multiplied them together.
And that's where the
That's where the other one, yt, that's where the squared comes from, and that's where y prime of t also went.
Gotcha. Okay.
Any questions? So what did we do there? We just picked a nice parameterization and then picked a description of area that suited our needs, right? And then computed the line integral instead of the double integral, because this time the line integral was easier. Any questions about that? No?
That seemed really convenient, like the sine squared plus cosine squared being 1, and then
Yeah, it was convenient because I chose this form. If I could have also written this like this.
that's because that equals 1.
Because
when you do the,
when I do the dp dq stuff, I get 1. So this will also work.
yeah,
But then I need to integrate something different. Let's just go see what happens if I do this instead, right? So I put an x of a cosine t times y prime of t dt. This is the integral from 0 to 2 pi of a cosine t y prime of t, which is b cosine t dt, right? And so now I've got ab integral 0 to 2 pi of cosine squared t dt. This is integrable. We know what this integral is. We have to compute it. We can use probably integration by parts. Yeah, we would use integration by parts. This is a complicated, not super complicated. Integration by parts will do it one time.
1 minus 2 cosine 2a, isn't it?
1 minus cosine 2a. Yeah, or we can do something like that, like some trig identity, right? But it's not as easy as just integrating this thing. And the point I'm trying to make is we have flexibility over our functions since we know the curve. So we chose the appropriate functions p and q that made integrating it as easy as possible with this given curve.
there are an infinite amount of variations of P and Q that could help any sort of
curve. There are an
question.
infinite number of choices for p and q such that dq dx minus dp dy is 1. So whatever my curve is, I can pick a different one.
Is there a way to find a dp dy minus or dq d or whatever it is? Is there a way to find a specific one that'll help your question?
No.
No? Okay.
No, you just essentially guess. And really, any one of them in practice, any one of them is fine. Because if you can just find one of them, then you can have the computer integrate. It doesn't really matter, right? And so when we have when medical imaging devices do stuff, they don't go and find different P's and Q's. They just pick the easiest one. They just pick one and then computationally estimate that integral.
But obviously some are easier than others.
True. Some are easier to estimate than others. But like to a computer, this and this, they're equivalent to estimate. Who cares? Right? To humans, we have to make one extra step and deal with this. But for a computer to estimate these integrals is trivial. So it doesn't bother picking one. It just does it. Okay? Does that make sense? Any questions about that? Are you sold on how cool Green's theorem is?
Can we do another example?
Yeah, we'll do lots of examples. So I want to go back to this example. I'm going to write it again so we have something different. But revisit this example. So this is C again, but now instead of going this way, I'm going to go backwards. Okay. So is this simple? Yes. Is it closed? Yes. Is it positively oriented? No. How do we deal with Green's theorem? Any ideas?
I have one, but it's kind of dumb.
I'm not going to say there are no dumb ideas, but let's hear your idea.
Maybe the way you orient dq dx and dp dy would change.
Sure.
Like it would still equal 1, but you could like switch them around or.
Well, it's not equal to 1, right? We already want to compute this integral. So the idea of changing the orientation is correct, but what do we want to reorient, right? So the plan is we want to make the curve go the other direction, essentially, right? So here we're doing this, but we really know how to do this using Green's theorem, right? So instead of C, we use minus C. So if C goes this way, minus C goes, am I out of pens? Where's my red pen? Minus C goes this way, right? And so this integral, the integral over C of x to the 4th dx, xy dy, this is equal to negative the integral over minus C of x to the 4th dx plus xy dy. Does that make sense? When I change the direction in which I go, I just get a negative sign, right? So I change the direction in which I go because I'm going around negative C. And so if I put a negative sign in front, that cancels me going the wrong direction. And so how do we proceed here? We use Green's theorem on this.
You should get the same answer though, right?
As our previous one? No, we're going to get negative the answer.
Well, okay, yeah.
Because our curve is going the opposite way.
Mhm.
Right, but if we just make a mistake, it's okay because we're gonna get the answer. It's just that we're gonna get with the negative sign.
Yeah. I mean, you're going to get a negative sign if it's not positively oriented. Correct. Any questions on this?
Would it be sufficient to reverse the limits of integration? That's the same as putting a minus sign before the integral, isn't it?
That's what I was thinking.
So yes and no. That is the same as putting a minus sign in front of it, right? But what is reversing the limits of integration on this curve mean, right? That means going backwards along the curve, right? So going backwards along the curve is essentially going backwards along the curve. Reversing the limits of integration is just going backwards along the curve. That's what this means, exactly. So that's on the parameterization level. Any other questions? Okay, so now there's one last bit about Green's theorem that we can do. So before I go to this extension of Green's theorem, there's lots of exercises in the book. Please do them. It requires some practice with Green's theorem to use it well. Okay, and as we've already said, it's foundational in modern science. It's the basis for most of Maxwell's equations, and physics, engineering as a whole. So you should get good and understand Green's theorem. But, so go do the problems. But let's look at regions like this. So this is a weird region. It's got a hole in it, right? What kind of region is this not?
Simple.
It's not simply connected. Simple is for curves. Simply connected is for regions, right? It's not simply connected because there's a hole in it. But Green's theorem can deal with holes. Okay, so how? Nick just said, right? Masterfully. That's how it deals with holes, right? Question, Nazer?
Oh, I was just gonna say, couldn't we just subtract the hole from there?
Well, we can subtract the hole if our question is surface area,
Oh.
right? But our question may not be surface area, right? If we want to compute the surface area here, yes, we use Green's theorem on the outside,
And on the inside.
and then on the inside, and then subtract them. That's great. That's if we care about surface area. But we may not always want surface area. So how does Green's theorem work on this situation? Well, on not simply connected regions. So now this is where we're going to have to do some orientation. What I mean by that is, this is my region D. This curve is positively oriented, right? Yes? How do I positively orient this curve?
The other way,
The other way. Why so?
because that would be facing your region, or it would be left of
Region
your
on my left, right?
Yeah.
So now I'm driving this way, my region is on the left. So I positively orient this curve like this. So I'm going to say C, this is C1 and this is C2, is the union. So D is this enclosed region. Its boundary is this curve and this curve. It has two curves on its boundary, right? And so now,
Okay, so you said like you reverse instead of the outside, you're taking the inside for the curve on the outside. But then for the one inside, you're taking the outside of that curve. Right?
But everything stays on the left. That's a cool
yeah,
part.
let me rephrase what I just said, because I don't quite understand what you said, and maybe you don't understand what I said. So to keep things positively oriented, I need to make sure my region, the shaded area, is always on the left. So if I'm on the outside part of it, to be on the left, it's got to be going this way. But if I'm on the inside part of it, to be on the left, I have to be going this way. Does that make sense, Maggie?
Okay, yeah.
Because if I'm on the inside and I go clockwise, counterclockwise, the region's on the right.
Yeah.
Okay. So Green's theorem still works here. And what does Green's theorem say at its heart? Can I take stuff from the inside, the region, and change it to an integral on the curves, on the boundary, right? But this boundary has two pieces. Okay? So to do this, we're going to do some surgery. Let's separate this region into two places. This is D prime. Well, I should have made a 1, but whatever. D double prime. Okay? And I'm going to continue this orientation. So let's say I'm on this dot. I go this way. I go this way. And when I get to this red part, I'm going to go down. Right? And then, look, this matched perfectly. And I get to this red part, I'm going to go down. And then I'm going to go here. So this is one curve.
It's clever.
Right? And I do the same thing over here. I'm going to use red this time. So here, I'm going to go clockwise. And when I get to here, I start going up. Right? Because that also fits right here. So I separate my boundary into I separate my region into two different regions with different boundaries.
Do those overlapping regions, like where they are pointing in the same direction, affect each other? Like, would you have to?
Yeah, we'll talk about that in just a moment.
Okay.
Okay. So does it make sense how I chopped up my region?
Yes, and now you can see how a baker's son came up with this. He was used to working with donuts.
Maybe.
Sorry.
Okay. So let's use Green's theorem on this bit right here, right? Use Green's theorem on D1. And D2. We know that integral over D, well, let's not do that. See, the integral, over D prime of dq dx minus dp dy dA, this is, by Green's theorem, the integral over whatever this thing is, right? This is my new curve. It's this part of C2 plus C1, P dx plus Q dy. Okay? And I'm purposely avoiding what the curve here is because we'll talk about it in just a moment. Okay? So we use Green's theorem on this region right here, and Green's theorem on this region right here. And we're going to add them together, right? Okay? And so D this plus this, right? So now, I have these two regions right here, and Nick said, what happens in the place they overlap? What do you think should happen? I'm integrating the same function over the same curve, except they're going opposite ways.
They should cancel out.
They should cancel out, just like we did before, right? They are equal to each other, but opposite in direction. So this part disappears, and this part disappears, right? So this curve really is this, but when we add it to this curve, which is this middle stuff disappears. So really all we need to do is integrate over this Green's theorem part, all of C, and all of C here. Does that make sense?
I have a question about curve 1 at the inside curve.
Yeah.
When we take like when we orient it to the left, we're kind of it's kind of like the area outside of that curve, right?
We can't really talk about area outside the curve because if C2 didn't exist, then there'd be infinite stuff out here.
Well, that's what I was gonna ask. Was like if C2 wasn't there, then like they're trying to define this without a second curve. Like
Well,
Going-
we couldn't,
yeah,
right? This would not happen without a second curve. Does that make sense? Does that answer your question?
I don't really know if it was a question. It was more just like trying to, because the original like curve 2 without, if it didn't have that hole in the middle, it would just be about finding the area on the inside of that.
Mhm.
With it oriented, like going to the left, everything on the inside of it, right?
Say that again.
So strictly just looking at curve 2,
Hmm.
following like oriented positively, like going around
Yep.
the curve, following it left, I guess, or just on the left of
Yeah.
the curve.
Yep.
That would be talking about the area on the inside of the curve.
Yes. Well, it's going to be integrating the function, whatever
Okay.
functions you have, over the region inside the curve. Yes.
Sorry, I'm removing a lot of words. to
Yeah,
the-
but they're not necessarily always area.
Okay. And then looking at curve 1, it's the same thing, but it's the outside of that, right?
Exactly. Uh-huh.
And that only works since we have curve 2.
Yes.
Okay.
So what does this say at the end? I'm going to add these two things up. And all it does is I essentially do this integral, p dx q dy, over the inside, plus the integral over the outside. So if I want to do Green's theorem on places with holes, I just got to do both boundaries separately. Okay, does that make sense? So one thing I want to say is this idea of this is really, really useful. We won't really, there are some nice examples of why this is useful later in the book. I didn't get to them, but it allows us to, in some senses, disregard what happens here. So let's say I have some really complicated region, but I'm really only interested in my function around some specific points, right? I can put a nice circle around a specific point that's very nice that I parameterize, and then I can compute the outside stuff and essentially get rid of it. So this allows me to sort of single out things that are of interest to me. Okay. Any questions before we go? No? Okay, we are good. Have a nice day.
Thank you, you too.
Thank you.